Hi, welcome to the second video of the second week. And in the first video, we talked about linear models, and in this video, we are going to talk about the analytical solution to the linear model. So, in this video, I'll be going through a practical problem while explaining the analytical solution and how to build a model with the analytical solution. So let's get ahead with that. And so here I will explain how the analytical solution to a linear model works. And all right. So let's start with what our linear model was. So we described our linear model as y equals x w plus b, where this described the weights and this described the bias. So for this linear model, we say that the analytical solution is analytical solution for this linear model is where we find the values for w and b. So now we can prove how to get w and b, but I feel like that's a little bit out of the scope for this particular subject. So we'll consider the given analytical solution, which is x hat transpose times x hat inverse times x hat transpose times y. It's a bit of a long and convoluted solution, but I'll show you how this is not that hard to calculate, right? And then for the bias, we have mu y minus mu x times w. So where I'll describe each of these variables as well. So mu y is the average of y. So let's say that average sum of y divided by n. Mu x is the same, and x hat is equal to x minus mu x, and y is equal to y minus mu y. Well, actually we don't need y hat here, so I'll just erase this. So now that we have these ready, I'm always covering something with myself. Alright, so now that this is ready, we can go ahead and look at how to train this model. Like, not really training, like how to define the model. So let's get into coding. So we are going to do this with Jupyter Notebook, and I think not too sure that this is whether this is big enough. Let me try to go full screen. And maybe I can increase the zoom a little bit. Right. I'll make this a little bit bigger again, as much as I can. All right. So, okay. Now let's see how we can code the linear model to an analytical solution. So for that, we are going to use this very famous dataset called the MNIST dataset, and we are going to follow these steps for model building. So first we read the data, then we pre-process the data, then we choose the appropriate model and build it, then training the model and evaluating the model. So this is sort of the steps we are going to follow throughout this course. And all right, let's go ahead and do our first step. So first we have to read the data. So for that, I'm going to do some necessary imports, and then the data reading part is quite easy here because it's already provided as a dataset by TensorFlow. So we are just going to say dataset datasets.mnist.load data, and there we have our data. And this dataset is already sort of separated into the training dataset and the testing dataset, and the data and the labels are also separated out for you. So we just need to get it in, sort of input it into a different variable so that we can use it later. And here I'm checking the sizes of each of the datasets to make sure that we have got it correctly. So all right, here we go. First I forgot to mention what the MNIST dataset is. So it is a set of handwritten digits from 0 to 9, and our idea is to separate these digits. All right, so what we have are handwritten digits. So like basically we have an image, and this image is 28 by 28 pixels as shown in the shape, and we have 60,000 such images in our training dataset. And the labels for the training dataset is again 60,000 by 1, because the label is answer to the question, what is this digit? So we'll have something like so let me, all right, so basically we'll have things like handwritten digit here, and then we will have the label as, no, that's not what I wanted to write. All right, so this is basically what the dataset looks like. Okay, sorry, some technical trouble. So this is our image given as 28 by 28 pixel image, and then we have a label, a single label describing what this image is. So let me find out photo from the MNIST dataset. And all right, let's, so this is a photo from the MNIST dataset, and you can see that each image is a black and white image of a handwritten digit, and it has a corresponding label. So in this case we'll have labels 4, 1, 0, and so on. Right, okay. Now I think another question you might get is like, oh, is this linear regression or is this linear classification? So we'll talk about that at the end of the video, and I'll show you why we consider this to be a linear regression problem. And most of linear regression problems are hard to solve analytically, and this is a problem that we can actually solve analytically to a good accuracy. So let's see how we go. So I would like you to I'd like to invite you to do this exercise with me, and yeah, like you can. I will provide this. I'll provide this Jupyter notebook to you so that you can use this, or you can get the idea and code on your own preferred coding interface. All right, so next what we have is a visualization of the data. So I'm printing 20 images here. So first 20 images in our training data set, so you can see. So this is the kind of the data we are dealing with. Now that we have an idea about the data, we can go ahead and do the pre-processing. So the first task we do is we reshape the data from a 28 by 28 image into a singular vector of size 784, which is 28 by 28. So if I'm to show you what's happening there, what we are doing is getting this image, which is 28 rows by 28 columns. We are going to sort of stack these rows horizontally and create a single row. Right, so this would be altogether 784. I believe that is correct. Let me check. 28 by 28 is equal to 784. All right, so that's what we are going to do. And having done that, next step is we are going to scale our data from the range of 0 to 255 into -1 to 1. So how we do that is we subtract 127.5 and then divided by 127.5 to achieve the range of -1 to 1. Right, so to explain that math, I believe that math is quite easy, but just in case, if we get a number, then we subtract 127.5 from that and divide 127.5. So if we take, for example, 0 minus 127.5 divided by the same would result in -1. Then to take the other end of the range, 255 minus 127.5 divided by the same would result in +1. So our range, which was from 0 to 255, would now convert into a range from -1 to +1. So this is much better for us to be dealing with. So for several reasons, because when you have large numbers like 255 here, when you do a lot of multiplications, this number could easily overflow, right? Because imagine like multiplying by 255 compared to multiplying by 1. So that is one of the reasons, and there are several other reasons to normalize the data into a range that is small. And you can choose not just this range -1 to +1. You may choose 0 to +1, or you can use the z-score. So yeah, like any acceptable statistical method, right? So all right, let's go back to the code. So okay, we'll run that and verify that it is properly scaled by looking at the minimum value and the maximum value here, and we'll also check the size of arrays, our training data and the testing data, to see whether we have successfully reshaped them. And having done that, we are going to do this thing that we call one-hot labeling. So, okay, back to the whiteboard to explain that. So, as I mentioned earlier, we have labels as individual numbers 1, 2, and so on until 9, or not to forget 0. The problem is these are individual numbers and this does not exist in a continuous range. So how do we convert this problem into a regression problem where we calculate a number in a continuous range? So what we do is, let's take one of our images. Let's see, let me try to find an MNIST image. All right, I'm gonna take a couple of images. Just bear with me for a moment. So we have the answer to each of these as 5 or 6. But what if we have the answer to this as a vector where the 0th element describes how much this image belongs to the label 0. So we know that 5 is not a 0, so 0. And let me have the index here. So in blue, like we have the index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we know that 5 does not belong to 1, not to 2, not to 3, not to 4, but 5 belongs to 5. And so on. And for 6 as well, we can come up with a labeling similar to the above, and we call this one-hot labeling. So why is this called one-hot labeling? Because one of these values is hot, which is 1, and the rest are not hot. That's the basic idea behind it. But the good thing about this system is now what we are doing is we are not predicting a category. What we are calculating now is the membership of this image into any of these categories. So that membership is a number. So 1 would mean that this handwritten digit belongs to this category 100%. So when we predict using our trained model, we may get something like 0.1, 0. Let's see, I'm gonna say 0.05, 0.05, blah blah blah, and then when it comes to the index 5, we may have something like 0.77, and all the rest are like really small numbers, right? So what we are going to check is, okay, which of these membership functions has the highest value? And if 5 has the highest membership value, that means, okay, this most probably belongs to the category 5. So that is how we convert this classification into a regression. Okay, now I think you understand one-hot labeling, so you can go back to our code. Alright, in our code we are going to do the one-hot labeling here. and we check a couple of data points to see whether the one hot labels have been achieved. And now we can build the model. And here we have given the same thing I gave you guys earlier, the linear model and its analytical solution. And we have the explanation of the variables here. And if you are interested in the derivations, you can follow this link and find the derivation as well. Okay, so something I didn't mention earlier is that x hat transpose by x hat is the covariance matrix of the data x. So that's not too important, just good to know. And let's calculate that covariance matrix, because that's the first part of our calculation here. What we are going to do is we are going to calculate the covariance of the matrix X, and we are going to inverse it and then multiply it by X hat transpose and Y. Right, so in order to calculate the covariance matrix, first we calculate our mu, both mu's, mu X and mu Y, and then here these are like X hat, X training hat is what I refer to as X training sub, another notation to mention the same thing. All right, so we will calculate all these and then calculate the covariance matrix as well, which we are defining with this parameter co-training. Sometimes it's a bit hard to pronounce the variable names because they're a bit short, but all right, let's go and calculate our covariance matrix. Now you can see that our covariance matrix is very, very small, and this is going to be a problem when we are going to attempt to take the inverse of it. So this is where we find that this is a singular matrix and we can't find the inverse. So we are going to do that with Eigen decomposition. So I believe you have already studied linear algebra of some sort, but I will give a little bit of a introduction as well. Right, so okay, back to the whiteboard. This is where we are going to learn about Eigen decomposition. So take a matrix A. If we can find a set of let's say if we can find a vector v and a constant lambda such that AV is equal to lambda v. So if we can find something like this, we call v eigenvectors, and lambda we call eigenvalues. So for this equation AV equals lambda v, there are, so if A is n by n matrix, there are n solutions, and n solutions means there's n eigenvectors and n corresponding eigenvalues. So this is about eigenvectors and eigenvalues. Okay, and so now following from this definition, what we can do is AV equals lambda v, and we can say that AQ is equal to Q capital lambda, where Q is the collection of such vectors and capital lambda is the collection of such constant. So this is a collection of eigenvectors, this is a collection of eigenvalues. So we can say that Q is equal to the column vector such that Q1, Q2, Q3, and Qn, and where Qi in 0 to n is the ith eigenvector of A, and capital lambda is simply the diagonal matrix whose elements are the eigenvalues. The ith eigenvalue, right? So now we have this definition as well. Let's go to the next page, and we had AQ is equal to Q lambda, and from that we can say that A is equal to Q lambda Q inverse, right? So basically here what we did is we multiplied both sides by inverse of the Q matrix, so that we have A times the identity matrix equal Q lambda Q inverse, and this means A equals Q lambda Q inverse, right? So I'm gonna erase that part because I don't think that's really needed. But now that we have this, what we can do is we can do another interesting thing, right? What if we turn this around? So what if we take the inverse on both sides? So what we can do is we can say A inverse is equal to Q lambda inverse Q inverse. So this way we can calculate the inverse of a matrix using this eigenvalue decomposition. But now you may have another question on okay, now it's good that we can calculate the inverse, but again we have to calculate two more inverses. So how can we do this? So I told you earlier that Q is the column vector of our eigenvectors, right? Column matrix of our eigenvectors. So we know from linear algebra that eigenvectors are orthogonal to each other. So let me say that eigenvectors are orthogonal to each other, and this means Q is an orthogonal matrix. And from matrix theory we know that Q, if it's an orthogonal matrix, Q's inverse is equal to the transpose of Q. Now that is much easier for us to calculate. And okay, another page. Now we know that A is equal to Q lambda inverse Q transpose. And now you may ask, how do we calculate lambda inverse? It's much easier than the rest, because we know for a diagonal matrix the inverse is where your diagonal is 1 under the value. So 1 under lambda 1, 1 under lambda 2, and up until 1 under lambda n. So this is how you calculate the inverse of lambda. So now we know that we can easily calculate A inverse. So this is all good, but we saw that previous attempt at inverting it was not successful because A was a singular matrix. Now what we can do is we can do a little trick here. We can add a really small value to these like our lambda values, our eigenvalues. So what we do is we say that lambda, so I'll go take a new page. Lambda is equal to, this is an assignment basically. We take lambda prime, which is equal to lambda plus a small coefficient where epsilon is small coefficient. You can see that epsilon is greater than 0. So this is a really small coefficient which we call a regularization coefficient. So let's go to this small regularization coefficient. Oh, right. Now let's go back to our code and we can do these interesting things. Linear algebra stuff quite easy to do when we use computational library like NumPy. So here we are calculating eigenvectors and eigenvalues, and we take the real part of it because it could be a complex number sometimes. We are only interested in the real parts, and we print them to see how it looks like. And to see whether our eigenvalue decomposition is done correctly, we calculate the eigen error by recreating our covariance metrics using the eigenvalues, and then we print the error, and we also inspect what are the maximum and minimum values within our eigenvalues. So let's see how that is, and we can see our maximum eigenvalue is quite big, but our minimum eigenvalue is very small. It's in order of 10 to the power of minus 12. So this is where we add our little regularization coefficient. This is tiny because, as you can see, it's 0.001, but it's big compared to our minimum eigenvalue. And using this regularization coefficient, we create our precision matrix, another name for the inverse of the covariance matrix. And to see whether our inverse is done correctly, we recalculate our covariance matrix, and to see whether we did this conversion or the inversion correctly, we multiply our precision matrix by our covariance matrix, and that should give us the identity matrix. So we subtract the whole thing from the we subtract the identity matrix from this whole thing, which should give us the identity matrix, and we print the error. So let's see. So the inversion error seems to be very small, so now we should be able to go ahead and sort of train the model. Like by training, we are just going to calculate W and B because this is the analytical solution. So let's calculate our weights and the bias using our formula that we learned earlier. So here we just print the maximum of the weights and the minimum of the weights just to see how the weights look like, and then we print our biases to see how they look like. They all seem to be fine, and now we are going to evaluate the model. How do we evaluate it? We use our calculated W and B on the training dataset. We use the equation x times W plus B is equal to Y. So we are creating our predictions based on the training dataset, and Then here we are printing it, and in this section what we are doing is we reconvert our one hot labels back into the range of 0 to 9, and then here we are calculating the accuracy of our training dataset, and similarly here we are calculating the accuracy for the test dataset. Alright, let's try what this gives. Okay, so our training accuracy is around 85%, and testing accuracy is around 86%. So this is not very great, because MNIST dataset is a very clear and concise dataset. But this was the analytical solution, and for a analytical solution, this accuracy is very good. So I invite all of you to try this. This notebook will be provided to you, and next time we'll look at a different regression problem where the analytical solution does not work, and with that we can also discuss what other solutions that we can use when the analytical solution does not work. So I forgot to come up with what's next slide this week, so let's go, and I'll write it down for you. I think I said up next. Up next, we'll be talking about gradient descent with a linear regressor. All right. See you at the next lecture, and please do try this analytical solution with MNIST. All right. Bye.